All right. Bayesian Cognitive Modeling. Here we go. Today's the first day that I'm going to try to run a job on my computer this while I am doing streaming. I unfortunately started a job. I want to just stop the job, but I just want it to run all day. So I'm just going to have to stream while that's happening and see what happens. Anyways, but you'll be glad to know it is a drift diffusion model. So, and it does involve doing Bayesian cognitive modeling, like what we do here. So let's get right into it. And so interestingly enough, it has to do with a hierarchical model. And it deals with data that could be modeled as a signal detection theory problem. Maybe, but you wouldn't want to do that for what I'm working with. So we're going to get right into it today. Welcome back. I'm excited to continue where we left off yesterday, where we had just gotten to extending our signal detection theory model to include random effects. I also got some Rolos, little candies. Alright. Alright. Let me pull up the code. Oh, actually, this might work. Mm-hmm. Someone more knowledgeable than me could probably answer this question, but I'm wondering if obviously I'm using computing power right now by running the code over here. But then I'm also running OBS. I don't have Dropbox open. I have Adobe open and Google Chrome open. I think I'll be fine. So let's just going back to what we saw yesterday. Basically what we're doing here is now we're capturing individual differences in our success, our discriminability and bias terms. Mm-hmm. Let me open the code. Excuse me. So let's just walk through this model then. K is going to be the success rate. Oh, we have data this time too. Let's load the data. Uh-oh. Bad restore file. Hmm. Forty subjects with each of their hit, misfire, what is it? We have their hit, correct rejection, false alarm, and miss. For each subject, like there is four. Some people are spot on. 8 trials in total. Oh, some people it looks like some people actually have more trials too. And this is for, right, we're looking at induction and deduction here. Paint the picture. 80 subjects. Each looked at 8 arguments, right? So induction here, 8 arguments. 8 arguments. So everyone looked at 8 arguments, yeah. Okay, I think I follow now. For each observation, right? Nice. Oh wow, so this is interesting. This is a for loop here. And we're going to do both data sets. And it ran. We're going to have to talk through this. Okay. So hits and false alarms, binomial distributed with these success rates. Success rates for the hits, false alarms. And each of which are distributed by the total number of trials for those things, which are going to be 40 each, right? 4. 40. What's 1 to 40? For a given trial, there's 40. Or there's 4 options, right? This is a reparameterization. So these success rates and false alarm rates are distributed. Fees, that's a probit. We take half the D minus the bias. So this is just the parameterization that describes this signal and false alarm rate. And then we get the posterior distributions for C, bias, and discriminability, which are distributed by mu and lambda instead of what we were doing before, which just involved setting like uniform priors for each. Now we set distributions for each, and we set priors for each of the corresponding parameters within the distributions for those. And we set relatively uninformative priors, and we just parameterize sigma here. Okay. Now here, we set the iteration and burn-in rate that are going to be used in these. And then for each data set, so if data set's 1, we use the induction data set, and then we extract the various parameters. So data set is 1, then we're going to get H, which is all the rows in column 1, all the rows in column 2, all the rows in column 3. So missing, hit, false, and what's the fourth one again? Some up here. Correct rejection. Okay. And we get the total counts. Which should be 4, right? Since if you had a correct rejection and a false, these should always equal 4. So all of these actually, all the N's and S's should be equal to 4. Nice. And since each subject has the same number of signal and noise trials as demonstrated here, we're just going to, instead of have this vector, we just assign the value a scalar here. So we're just assigning like a single cell vector instead of using this length 40. There's like no point. And then this gives us the number of data items, which is 40 for each of the 2 induction and deduction data sets. So if we're in one data set, right, because we're doing a for loop here, this just needs to give us the number of items in that or observations in the data set. We're going to take all of that, and then we're going to initialize the parameters here. So what do we need? We need parameters for mu and lambda for our random, for our distributions in the hierarchy. and then discriminability and bias. And then what we're interested in looking at here is just the average discriminability, average bias, and then the variability surrounding those estimates. Right, so we don't care about any individual subjects. In this case, we care about the averages. We're going to do so for both data sets. And then here is just pulling a random sample of 1,000 iterations from, or making a random sampler that we're going to use to just keep a random sample of these to plot for plotting. And here's the plot. So we're going to end up with distributions here. So you can see there's discriminability for the deductive and discriminability for inductive, and these values are corresponding to the distribution. The posterior distribution is represented here on the graph, where discriminability, higher discriminability, thus the gray color here indicates the deductive. So deductive arguments more discriminative than inductive. Maybe that's part of the logic-y portion or something like that. Oh. Hey, hi. You want to say hi to stream? Oh, wait, let me turn you around. What's up? My partner says hi, stream. Hey, hon. Okay, nice stream. Sorry, the coordinate. Okay. So here are the distributions, and this is the joint posterior distribution for the two averages for bias and discriminability. And you can see that let's see. What can you see? That there's more bias in the deductive. There's less bias in the deductive, and though more discriminability. The variability in right, but there's the probability that there's no bias in the in deductive here. Use the sigma crosses 0. Does it? That's close. I guess it doesn't. No, it's just close. Oh, I'm looking at the wrong thing. This is mu. This is the distribution of mu. Distribution of the average bias, which here indicates that within the 80% credible interval, there's a probability of there being 0 bias. And part of that then tells me why the distribution for the discriminability is so large. Well, what does negative C mean? Because both are C are negative on average. And keep in mind, let's see, negative C is, let's see, negative values of C correspond to bias towards saying yes. There's increased bias towards saying yes for inductive arguments. That's interesting. So while deductive arguments might be more discriminable, inductive arguments are people are more likely to say yes to them. Okay. Of key interest to RIPS 21, conjecture is how group level means for bias, that's C, and especially discriminability differ between induction and inductive conditions. Is this true? I would say it's true. I don't recall if there's something I can do to explicitly test that right now. I don't think so. I think it's more of a posterior predictive check kind of thing. Look at samples generated. Yeah. Well, let me think. If you do, I think I have something. I'm just looking for some code to think about. Like, if I take the mean of imud and I take the mean of dmud, I think this is what I do. So I can just ask, is dmud, how many times often is I'm dmud bigger than dmud? And the probability is near 1, so it's large, right? And then likewise, you could do like dc deductive's light. Deductive is larger, has larger discriminability, and has less bias. Right, you just check the, I'm just doing the logical here. I think this is how you do it, but see, this get a bunch of trues and falses, and then I'm just asking, well, how many, what's the probability, what's the average here? And on average, this statement is true over the span of 1,000 samples, right? This is like, not all of the samples though. No, it's like 9,000. Nice. I think that's the answer. Okay. Oh. In Rotello, use standard significant testing methods on their data to reject the null. That there was no difference between discriminability for induction and deduction. Their analysis involved calculating the average discriminability for each subject using edge corrections where perfect performance was observed. These discriminabilities gave average and by calculating via the t-statistic and so assuming associated Gaussian sampling distributions and observing that the p-value is less than 0.01, rejecting a null of equal means. This finding of different discriminability provides evidence against the criterion shifting unidimensional account. No, this is not consistent with the Bayesian analysis I got. So I find that discriminability for deductive is on average larger than that of the inductive. So I got the opposite findings. If the point of this question is just to me to show, right, because I found here that there's definitely a significant difference between the two, though the difference that I observed is one where values for discriminability for the inductive condition are, or deductive condition, are larger. And in fact, let's see. They've got deductive but they did these weird removal of trials, right? Calculating discriminability for each using edge corrections. Okay, so like probe it or something, like inflated. Well, I didn't have to use edge corrections. I just used the data. Your edge corrections must have done something to the results. Okay, rerun the analysis without. Huh. Okay. Maybe I can get the trace plots too. So turn the burn-ins to 0. Run this again. And what this is going to do is induce autocorrelations between the two variables. Oh, I just also just don't get as vicious of results as they do. Maybe I'll restart the plot. Which is sort of this, but Mm. If I do like, see, I still get reasonable results every time. Bring it with me. I change the initial value and I change the burn-ins. Still, even only a little bit. Yeah. I don't get that. I don't get this extreme sort of issue in the sampling. But so why this would be the case? It would have to do with the autocorrelations in the chain. Then you can ask why again, and part of that would be, well, let's see. The sampling would be inducing a relationship between the two, maybe a larger relationship than what the sort of dependence that, unfortunately, I want to use the word emerges out of iterating over multiple samples over time. Yeah. So the answer here is it's due to autocorrelations. The particular things that are being autocorrelated looks like they got stuck somewhere, right? So when the average discriminability is something, the average bias was something, maybe. I'll change them to something outrageous. Let's see what happens. Even 50 and 50 doesn't look like I'm generating. Yeah. The evidence seems to be pretty strong here. And the autocorrelation doesn't seem to be an issue as much as an issue as the textbook has indicated. Could possibly be an issue. or at least this newer code is fine. But when that is an issue, there's a problem of correlation between the variables here, where based on some initialization of the values are like showing this systematic pattern, and they're getting stuck in some like local minimum here or something, or some like stuck around some value, right? So in the space of probable values. So in cases like this, we would need more samples. Even just 1,000 samples in the house. Penny loafers. Yeah. So we get solid results no matter what. So I would have to dig into, well, what could possibly be one of the associations that could be driving this sort of like systematic systematic sampling in areas of the distribution like this. So the last sample was highly dependent on the sample that came after it. If we're talking about extracting samples from the MCMC or the Gibbs sampler in this, which is, yeah. But that's the extent of what's going on there. So let's see what happens now. Parameter expansion. Okay. So even after the introduction of a burn-in period, there's sampling issues with the way the chains in the hierarchical variance parameter here are behaving. Oh. I'm just looking for. Oh, nice. Okay. It looks like. I found the. I can just use trace plot here. And I want to look at I samples. There's deviance. There. Here, you see. This is what it's talking about. So turn the burn-in to 0. And then we took a look at the trace plot of I samples. This is, see, it looks more systematic there. Like that. Dependency. We want something more, looks like noise. from CMC plots. I think I found a package that might be helpful. Oh, sick. So now we're looking at a single chain here. You can notice how, like if you saw the deviance chain, for example, just to use an example of a good mixing, or the mu chain, you see it's very much, but here there's more, there's like a pattern underlying it. And that's a problem. This is better, but still we want to remove those dependencies, or those autocorrelations. This is pretty cool though. I'm gonna do MCMC plot, and this will give me I think this will give me the, oh nice, it just spits me an output over here. You can see the autocorrelations then. So look at the autocorrelations for sigma. Let's see. You see this? See, this is what we're talking about here. See how it moves together? And you can also evidence here. I'm just looking at the autocorrelations. That's useful. As shown. Alright, parameter expansion. This is a trap, it's called. Okay, so when if the variance is really low and sample's really low, then that iteration of low sample of low variance makes it so that the next one is likely to be low, and you're stuck in this like pool of low for the parameter because the variance that you iterated over is low, or like in this, it's in this low spot. So in order to escape those sorts of traps where you're estimating or you're sampling in this area of the parameter space where sigma is close to 0, augmenting the original model with redundant multiplicative parameters. Specifically, we can extend the hierarchical signal detection model with 2 multiplicative parameters. You see that? And you see this. This mirrors what we saw when we were looking at the chain. The role of these additional parameters. So we're going to rescale C and D. So that they're sigma parameters. So we're trying to prevent this near zero bias sampling. So that this variance trap, if you will, because it can create issues of autocorrelation, autocorrelative samples for our sigma parameters. So the graphical model that implements this parameter expanded model is shown here. Note that the new model is equivalent to the original because it simply reparameterizes the model. Okay, so we can do like a next to text thing here, where if I pull up the model here, and I pull this down, done. If we just side by side it, you see nothing really changes up there, but then you're seeing here when we're parameterizing discriminability and bias, we're adding this additional step, and then we have to set some priors here, some parameters. All right, so what we're doing is C and D are going to be equal to so instead of C and D being normally distributed Gaussian distribution with mu lambda, now C and D are mu plus XIC XID times these. So we have this little prior distribution here, uninformative, that is like a multiplicative sort of thing. Right, so since it's uninformative, it's not changing the results, but the parameterization helps escape situations where we have these variance traps. It's pretty clever. Did we change the parameter for gamma? Okay, gamma less precision. So it looks like we also changed our priors here for gamma. But we're centered on 0 here. So notice that each of these distributions for the sigma parameters, or the deltas now. It's interesting. This still ends up with the same results, right? But we're helping prevent, or it's the same parameterization. It's attempting to get at the same question. So in the parameter expanded, so this is parameter expansion, remember. So in the parameter expanded model, bias and sigma for bias are rescaled by multiplying by delta. The parameter is now expressed here with mu, delta, and man, I just really blanking on the name of that one. Gamma, maybe? Or delta. Oh, that's delta. Yeah, I'm getting lost in the symbols. Zeta. Zeta and delta, yeah. Right, so we have these zetas here with the deltas. So zeta gets multiplied by delta, and that is supposed to be represent what? So a new sigma. Something I didn't notice either was the sigmas down here. So instead of having these just sigma parameterizations, now we have sigma new. So we have the new sigmas, right? And then these new sigmas, so we derive these new signals from the lambdas, just like before, how we would normally do. However, we then take these parameters and we multiply them by this absolute value of this zeta term. So we estimate the zeta term and we multiply it by that. So if we got 0 here, we multiply with this. Does this guarantee we're gonna not get zeros? Or so what's the rationale behind parameter expansion? Is that updating zetas includes additional random components. All right, so we're introducing additional stochasticity into the model so that we're decreasing the likelihood that we're going to be getting these zeros over and over again. Right? So doing so helps prevent the chains being stuck in these zones. So in doing so, though, we need to make sure that we're then rescaling back. Is that? So we just can't interpret the new sigma nu. We have to interpret sigma nu multiplied by the absolute value of our parameter expansive or parameter expansion tool. I guess that's what I call it. Here's the graphical model. And then it removes, what we would see is that we have less of the variance trap occurring. So we have within subjects, we're going to have a given person who, and this is for one data set. This is for a person who, say you have 4 observations, right? For each of the hits and the false rates, you'll get these false and you'll get the hit rate and the false positive rate for each subject, which informs the discriminability for that given subject and the bias for that given subject, which are derived from a group average, so a group of mean and average discriminability. However, now for sigma, in order to prevent the variance trap and incorporate parameter expansion, we also have zetas that are within each subject, right? So each subject is going to have a zeta term, which is also distributed by a mean-centered Gaussian distribution with uninformative prior distributions. These uninformative prior distributions then can be reparameterized into sigma by introducing the stochasticity term. So what's delta? Wait, I'm missing something then. Delta is the term that gets used, some multiplicative term here. Okay, so delta gets multiplied by zeta. Alright, so here, delta and zeta make up this. So we say that variances are from a distribution of variances, and that this distribution of variances for a given subject combined with some randomness term across the groups gives us a value for this, but also gives us estimates of sigma for bias and discriminability that are not as susceptible to zero variance traps in the sampling. Okay. Divided by. These are the new sigmas, and then to get our sigmas. So these are new sigmas, right? But then to get our sigmas that we use, the scaled sigmas we use, multiply the absolute value of our zeta stochasticity term by sigma. And that gives us the properly scaled sigmas. So we get our results back. What are the questions? So this is the last question. Okay. Experiment with different priors for the unscaled precision. Ah. These terms. And the scaling parameters. These terms. Okay, let's run and let's do it. What am I looking for? See that? Little hiccup there. In the induction sample. Looks like as we continue to more and more precision means what? Less stochasticity. So a less diffuse estimate of precision makes it so that is sigma for the bias term. At gamma, we're getting biased estimates when we do gamma this low. Let's go back to the standard issue. With the uniforms 0, 1. Let's see what happens now. So far, it looks like changing the priors for the gamma distribution for our precision impacts or influences the results. We just get a little tighter. What if we do normal distribution? Looks like we get longer tails. But even there you see a little suspect. Let's do something with the variability. With samples, with priors that don't allow us to have a diffuse enough amount of probability. Then we get trapped in the zero variance traps, it looks like. So it looks like the scaling parameter matters less. But gamma, shucks. Gamma definitely matters. If gamma is too low, then the variability here is too precise and we're susceptible to more the traps. So we make this less precise, add a little stochasticity, and we get the same results. Distributions are just longer. It's interesting. So that seems to be the solution here, or the answer with that. The scaling parameter matters less. It's more about also changing the gamma parameter so that we sample sufficiently, or we have a sufficient size or diffuse sample for the lambda in our delta indicators here. Yeah. These. So these need to be bigger. Or these need to be diffuse enough. And the scale parameter matters less here. It looks like. Alright. That's it for today. And we're going to start with psychophysical functions tomorrow. So I look forward to get started on a new example. Yeah. And I'll catch you guys tomorrow. Thanks for tuning in. Oh, yeah. So, just a recap. I'll do a recap. So just to recap then, we went through and we incorporated a hierarchical structure into our signal detection theory model. And then from that, we noticed that we were getting issues, or there was the potential for us to get issues related to autocorrelative problems here, where we're somehow getting stuck in these zero variance traps for our sigma parameters, and that is impacting our posterior distributions here due to the dependency in the sampling. So we use this technique called parameter expansion, which is just a means for reparameterizing the model in order to introduce additional stochasticity, which we can then rescale back to give us the same sort of interpretation for the parameters that we ended up transforming. However, we are no longer being impacted by the potential dependency between the samples in our chain for the variance parameters. Cool. And it adds more to the model. So it's just a way for us to switch around some things, but it's not changing the interpretation, right? That's an important thing. So yeah, we'll move into the next example tomorrow then. Yeah. See ya.